Okay, welcome back. It's my pleasure to say that our next speaker is Marithania Silvero from Seville, and she will tell us about detecting positivity from link homology.
Oops. It's recorded, so. Okay, so thank you very much to the organizers for giving me the opportunity to present this work here. It is wonderful to be back in Warsaw after 6 years. So I was postdoc here at INFAM for 1 year in 2017. It was my first postdoc, and I was under the supervision of Maciek Wojcik. So I want to take this opportunity to tell thank you to Maciek and to Wojtek, who took care of me super well here, and I learned a lot from them, so thank you. And well, let's go now to the talk. The talk is about knots and homologies. I'm going to explain a criteria to extract positivity of links based on Kobanov homology. So this is joint work with Mark Kegel, Nagesh Manikandan, and Leo Musso. What happened?
Let's see.
Yes, so these are them, okay? The three are from the university, Humboldt University at Berlin. And well, I'm this one. And this is Mark, Nagesh, me, and Leo. So this is in Swiss NOS conference in Regensburg in Germany. But yeah, this is where we finished this. We were talking about this project and finishing it. So this is the structure of the talk. I will start with some preliminaries on positivity and on Kobanov homology. I will give a super quick definition on different notions of positivity that we are going to use, and I will explain Kobanov homology in a nutshell. Yes, I know in this semester many people have spoken about Kobanov homology, so I will give it a very brief explanation about it. Then we will explain the main result that we got here in the section 2, Kobanov homology of positive links. And then we will see in the third section how we try to extend our results and which examples and which families we could extend them to. So let's start with positivity. So we start with the braid group presentation given by Artin in 1925. This is I assume all of you are familiar with this. This is the presentation given by Artin. These are the generators, sigma 1 till sigma n minus 1, where sigma I means just a crossing between strands in position I and I plus 1. So strand in position I plus 1 goes in front of strands in position I. If you have the inverse, then the other one is the one going in front of the other. And these are the two relations. So you have sigma I, sigma j commute if they are far away. And sigma I plus 1, sigma I equals sigma I plus 1, sigma I plus 1. As you can see here, this is kind of Rademacher 3 move. So this is the usual presentation of braid group on n strands. So we say that a word is positive if it is written in Artin generators with positive exponent. So if you have a positive word in Artin generators, a positive Artin word, then what you have is an Artin positive braid. So a positive braid is a braid that can be written can be represented by a positive word. So for example, if we have this braid and we say, is this braid Artin positive? I'm using the word Artin because later we will see another presentation of the word group. So is this braid Artin positive? You see here that you have negative exponents, so this word is not positive. But using braid relations, you see that sigma 2, sigma 1, sigma 2 minus 1 equals sigma 1 minus 1, sigma 2, sigma 1, kind of these Rademacher 3 moves we were saying. Now here, sigma 3, sigma 1, they are far away, so they commute, and you get this. And now just sigma 1 minus 1, they cancel, meaning you use Rademacher 2, so you get this. And this word is positive, so beta is an Artin positive braid. So it's not trivial in principle to see if a braid is positive or not, but you understand the definition. This is how it goes. Okay, so we have this presentation of the braid group, and we also have this presentation introduced by Birman, Ko, and Lee in 1998. Here the generators are sigma Rs, where again RS means a crossing of strands in position R and S, with the last one, the S, passing in front of the one in position R, and the inverse is the other one, the one passing in front of it. And now strands can be far away. For this you need two letters. Here you need just one, here you need two, and the relations are these ones. The first one is telling you that if the crossings are, let's say, nested, then they commute, like this one can slice below this. And it's also telling you that if they are far away, they commute. This is the first relation. And the second relation is this one, telling you that, well, you can slice this crossing here, so you get something like this. This is equivalent to this, and this is equivalent to this. So this is the second relation, okay? And, well, here again, we can speak about a positive BKL, Birman-Ko-Lee word, if it is a word, a positive word in terms, I mean, you can write it in terms of Birman-Ko-Lee generators using just positive exponents, and a BKL positive braid is a braid which can be represented by a positive BKL word. So, we have arcing positive braids, this is an example. We have BKL positive braids, this is an example. And now if you close it, you have a closed arcing positive braid, and what you get is a braid positive link. So in other words, a link is said to be braid positive is it can be represented as a closed positive braid in terms of arcing generators. So if you have BKL positive braid, then you can close them exactly the same. And what you get, well, we could have called it BKL positive links, but these links were studied and introduced by Lee Rudolph, and he called them strongly quasi-positive links. So these links are called strongly quasi-positive, the ones that are can be represented by a closed BKL positive braid. So if we want to see how these families are related, it is clear that arcing braid positive links are strongly quasi-positive, because just take the generators having both strands together. This is trivial. And now we have another notion of positivity, which are positive diagrams, which are those diagrams that where all crossings, the diagrams are oriented and all crossings are like the green one, meaning that if you walk over and look down, then the arrow goes to the left. So this is a positive diagram, and a positive link is a link that can be represented by a positive diagram. So if you want to see this family in the picture, you get something like this. Braid positive links are positive, and positive links are strongly quasi-positive. So that this family is positive, it is straightforward. Just orient this and you will see that all these crossings are positive. So this inclusion is trivial. And that positive links are strongly quasi-positive, it is not straightforward. Lee Rudolph proved that. And the problem, this is positive, but these crossings here are negative. So this is where the problem and the complication arises. So you need to work with this diagram, with this representation, to get a positive diagram. But Lee Rudolph did proved that positive are strongly quasi-positive. But these inclusions are really inclusions, meaning that you have examples of strongly quasi-positive links that are not positive, and positive links that are not braid positive. So these are the three notions of positivity that we are going to deal with in this talk. Okay, we have braid positive, positive, and strongly quasi-positive links. Okay, so this was all about positivity. Now let's see a very quick review on quantum homology. So, quantum homology, as you know, is a link invariant. It's a big-graded homology introduced by Kovanov in 2000. It's category 5 Jones polynomial, and it's a stronger invariant. For example, these two knots have the same Jones polynomial, but their Kovanov homology tables are different. And the reason is that these terms here cancel, and here, of these three, just one survives, which matches this one. So, yeah, this is it's a stronger invariant than Jones polynomial. It detects the ang knot, the right-handed trefoil, the left-handed trefoil, figure 8 knot, the 5-1, and other knots. It also detects the two components trivial link, and with Kovanov homology you can get many topological and geometric information about the links. In particular, with the S invariant that can be computed from Kovanov homology, you can get it is possible to get a combinatorial proof of the topological Milnor conjecture about the slice genus of torus knots. So, This is command of homology, so if you want to see how to define it, well, we need to construct the chain complex, we need to define the chain groups, the abelian groups, and we need to define the differential. And once you have this, then you take the quotient and you get the homology groups, and this is command of homology. So the question, if you want to understand command of homology, you want to define it, is, okay, how do we define the command of complex? Who are the chain groups and who are the differentials? So just very quick explanation on this. We start with Kaufman states, so this is just a way to associate. When you have a diagram, you associate a label, either a 1 or a 0, to each crossing of the diagram. So here we have 3 crossings, 1, 2, 3. So to each of them we associate either a 1 or a 0. So in this case I have chosen, for example, this one I associate a 1, a 0, and a 1. In total, if you have C crossings, you have 2 to the C possible states. And I'm going to encode them, like if I'm ordering the crossings 1, 2, 3, I say that 1, 0, 1 means that to crossing 1 I associate a 1 label, to crossing 2 a 0 label, and to crossing 3 a 1 label. And once you have this, as you know and had been said before, you just smooth the crossing following the label. A 0 label will be something like that, and a 1 label will be something like that. And we keep the place where there was a crossing, I will put this segment. So if you do this there, you get a set of circles with some chords. So this is the smoothing of this state. If, for example, you consider state 0, 0, 0, you will get something like this. Okay, so these are Kaufman states. So once you have a diagram, what we do, we consider all possible states, or possible 2 to the Z power states, and we arrange them in the way shown here. So in the first column, we put the only state having just 0 labels. Then in the second column, the states having just one label. In the next one, the states having 2 1 labels. And at the end, the only states having just 1 labels. So you get something like this. And I'm drawing an edge between the states that differ just in 1 coordinate. So 0, 0, 0 is connected to these 3. But for example, 0, 1, 0 is not connected to this one, because here you need to change 3 labels to get from here to here. So this is what is called the cube of resolutions. And now we are going to associate a copy of V. V is going to be a graded vector space generated by V minus and V plus, so it has 2 generators. And this one will have grading minus 1 and this one grading 1. So we associate a copy of V to each of the circles in the state. So here you have 2 circles, you have V tensor product V, here 1 copy, you see, right? Here you have 3 copies of V's. And the chain groups are going to be just the sum taken over all columns. So these are the chain groups. And now to define the differential, which is the only thing that is left, just realize that each time you change a label, a 0 for a 1, you are either merging 2 circles into 1, or you are splitting 1 circle into 2. So you have these 2 possibilities, either you merge or you split. So in the first case, you have 2 copies of V's going to 1 copy of V. So the differential, if you have B plus times B plus, this will go to B plus and B minus B plus will go to B minus, and B minus will go to 0. This is what we call the multiplication. And if you have a splitting, then we have this co-multiplication, sending B plus to plus minus plus minus plus. And if you have B minus, you send it here. So the differential is going to be defined on each edge of the cube by either multiplication or co-multiplication, depending on whether you have a merging or a splitting. And then you have to add some signs so that it's really, in each phase, it's really anti-commute, so you get really a differential. So in our example, you will get, for example, here, from going from here to here. Here you are splitting 1 circle into 2, so this is a co-multiplication. And in the other circle, you just apply the identity, because it's far away from the label you are changing, okay? So this is the differential in the Kovanov complex. So remember we said it is sub-graded invariant. So the first grading, the I grading, the homological grading, depends just on the column where you are, meaning the number of ones you have in the state. And the second grading, the quantum grading, depends on the positive and negative crossings, on the number of ones you have, and also it depends on this internal grading that we have in V, in the graded vector space. So once you have this, you can define, you have a complex, a chain complex, you can define the quotient, and what Kovanov proved was that these are in fact link invariant. So we can speak about Kovanov homology groups of the link. And this is the definition of Kovanov homology. Very fast, but this is how it works. And now, Kovanov homology of a link looks something like this. We represent it in a table. So this is Kovanov homology of the trefoil knot. And very important for the rest of the talk, this is homological grading, and it jumps in one unit. So I is homological grading, and the vertical one is the J, is quantum grading. Okay? So how we interpret this table, we say that Kovanov homology in homological grading 0 and quantum grading 3 of trefoil is Z. The same here, for example, this is the 2 is Kovanov homology of trefoil in homological grading 3 and quantum grading 7. And this is how you treat the table. And just if you want to recover Young's polynomial, you just have to say, okay, forget about torsion groups and just keep the free part. And now you say, okay, this one is giving -1 to the 0 power, meaning positive sign, times q to the first power, meaning this q. For example, this one is giving us -1 to the third power, meaning negative sign, times q to the nth power. So this is -q to the 9th. And this is how Kovanov homology categorifies Young's polynomial. Okay, so this was all about preliminaries. Now let's go to the new results on Kovanov homology of positive links. So the first thing we need to recall is some notation we are going to use. So we have a diagram. For example, this is a diagram of knot 10-165. So we can do a need safer smoothing, meaning that you just smooth every crossing in the unique way following orientation. This has nothing to do with A or B smoothing. This is just smoothing following orientation, the only one preserving orientation. And you get a set of circles with some chords in the places where there was a crossing. And now just construct safer graph, meaning that to each circle you associate a vertex. So we have 5 circles, so we have 5 vertices. And now you draw an edge connecting 2 vertices for each chord in the safer smoothing connecting 2 circles. So for example here, green and yellow are connected by 4 edges, so here you have 4, okay? And well, this is safer graph, okay? And we call it GD. Of course, here you are losing information because you don't see if the circles are nested or not. You don't know the relative position of the crossings, whether they are like alternating in the diagram or they are all put together. But this is safer graph. And now we consider reduced safer graph that we denote that way is just take all multi-edges and collapse them to a unique edge. So this is the reduced safer graph. Just if you have multi-edges, collapse them. So this is the reduced safer graph associated to this diagram. Of course, this graph is not a link invariant. This depends on the diagram you started with. Okay, so once we have a graph, we are going to write P1 for the cyclomatic number of this graph, meaning the minimal number of edges that you have to delete in this reduced graph to remove all cycles. So imagine we have this graph, cyclomatic number is 4, because you just remove these 4 edges and you get a tree. And you cannot remove 3 edges to get a tree, so this is the minimal number of edges you have to remove, okay? So P1 of a diagram is the minimal number of edges you have to delete in this reduced graph to get a tree, okay? So our first result is this one, that if you have a positive link, then Kovanov homology in the homological grading 1, this means the column, like homological is column, so the column indexed by 1 is trivial, but in one position where you get Z to the P1 number that we define, Z to the P1 power in this quantum grading. In the other quantum gradients is trivial, but you have just one place where it might be non-trivial. In this quantum grading, you will get P1 copies of Z. You can say, okay, you defined P1 of a diagram, but here you're speaking about P1 of a link. What is P1 of a link? Okay, take any positive diagram of the link, do this construction, And for all positive diagrams, this number will be the same. So this is the number we put here. Since the link is positive, just take whatever positive diagram you want of the link, do this construction, and this is P1. So this is an invariant, okay? An invariant because we are defining it for positive links, okay?
What is chi of L?
What, sorry?
Chi.
Oh, sorry. This is the Euler's characteristic of the, let's say, the maximal Euler characteristic taken among all Seyfert surface of the link. Or if you want, you can also think of it in terms of the genus, minimizing genus surface and translate it to the genus. So this is Euler characteristic of a minimizing genus Seyfert surface for the link. Yeah, it is. So sorry, yes, I should have said this before. Thank you. So this is the theorem, and now I'm going to tell you how we prove the theorem, because in the proof there were some steps that some results we got that I think are interesting themselves. So the first thing we needed for the proof was to prove this theorem, saying that if we have D is a reduced positive diagram, reduced meaning that you don't have nugatory crossings, okay? So if D is a reduced positive diagram and D prime is a positive diagram such that the Seyfert graph associated to D prime equals the reduced Seyfert graph associated to D, then their first Covan of homology are the same. There is some shifting. The columns are the same, are equal, but maybe they are a little bit shifted, meaning that the non-trivial group may be shifted, but the column is the same. So let's see an example. Imagine this is D. This is a reduced positive diagram. We compute the Seyfert smoothing. We get this. Now we compute Seyfert graph. Is this one? Just trust me, okay? You get this. And now the reduced Seyfert graph, just remove all multiple edges, so you get this. And now consider this diagram, D prime, it is positive. And if you compute this Seyfert smoothing, you get this. You compute the Seyfert graph, you get this. So yes, this one, the reduced diagram associated to this one equals the Seyfert graph associated to this one. So they satisfy the hypothesis. So, well, this was this node 12 and 110. This is this link. So, according to our results, their first Covan of homology should agree. And in fact, if you go to Node Atlas and check, yes, their first Covan of homology. When I say first Covan of homology, I mean in the column indexed by 1, they agree. And I told you that there was a small shifting. So, what is the shifting? Okay, this is for J equals 7, for quantum gradient 7s, meaning that the non-trivial group is at level 7. In this one, the non-trivial group is at level 2. So why this 5 distance, this gap? This was the graph that you got for this, not the reduced one, but the Seyfert graph you got. This is the Seyfert graph for this. So from going from this to this, you have to delete 5 edges. So this 5 is the shifting. So the shifting is given by the number of edges you have to remove to have this equality here. Okay? So this was the first ingredient in the proof of the result I told you. The second ingredient is noticing that this diagram here, this positive diagram, if I'm given a reduced positive diagram, I can always find a positive diagram satisfying this condition in such a way that this T prime is alternating and in such a way that the signature of L prime, meaning the link represented by this T prime, equals P1. P1, remember, the cyclomatic number, the number of edges you have to remove to break all cycles. And to get this, we use a result by Pavel Tracik, saying how, when you have an alternating diagram, how signature changes when you smooth a crossing by following a 0 or a 1 smoothing. So using this result by Pavel, we prove this. This was the second ingredient. And now remember, this was what we wanted to prove. We were trying to prove this theorem. So now we just say, okay, I want to compute Covan of homology of my link L, my positive link L. So by theorem 1, I know that I can do this, I can construct this D prime and they have the same first Covan of homology with some shifting. And now, since I can find this D prime to be alternating by the second ingredient, I use a result by Lee saying that alternating links are thin, meaning that their Covan of homology is trivial everywhere but in two diagonals, and this diagonal is signature plus 1 and signature plus 3. So since signature is P1, I know that all groups are trivial but this and this. And now to get this one, I use a result because these links are semi-adequate, so instead of looking to the column, I can look to the row, and there is a result by Joseph Shititsky and Radmila Satanovic that later we generalize in a joint paper, saying that this group has to be this one. And now to show that this is 0, we also needed to develop some lemma using the Kovanov-Skene sequence to show that in fact this group is trivial. So we get the proof of the result. So this is how we prove the result. I wanted to tell you this because I find this theorem also like interesting. And okay, so we have proved a result. And then next thing, other result that we prove is, okay, Covan of homology doesn't detect fiberness, so there are links, there are examples of knots, one being fiber, other not being fiber, but their Covan of homology is the same. So Covan of homology doesn't detect fiberness, but we prove that if you are just consider positive links, Covan of homology detects fiberness among positive links. So this is our result. If you have a positive link, then the link is fiber if and only if its first Covan of homology is trivial. To do this, we use our previous result and just show that here D prime can be chosen to be the trivial knot. So you know that the first Covan of homology of trivial knot is trivial, and this is how we got this result. So this result can be interpreted as a criteria to abstract positivity. Why? Because usually the algorithms that are known to detect positivity are not very good, but the ones that detect fiberness are more or less okay. So there are examples of knots. For example, this one, this is this knot in census list. So this knot is not fiber, and it was not known whether it was positive or not. So we compute its Covan of homology and its Covan of homology table. Of course, this we did with NotJob, with the computer program. Its Covan of homology table is this one. So you see that this one is trivial. So if this one is trivial, the link is not fiber, so then it cannot be positive, because otherwise our theorem will be false, okay? So this we can interpret as a criteria to abstract positivity. And you may say, okay, but sorry, for the moment, yeah, okay, so we interpret this that way. And this is what we have, the three different notions of positivity we were dealing with, and you can say, okay, what was known before? So Marko Stosic proved in 2010 that if the link is braid positive, then its first Covan of homology is trivial. And this was our inspiration starting point. In fact, his proof was really useful for the proof we did. So what we did, if we want to put fiberness in this picture, this is what we proved, the one I have just told you. So if we want to put fiberness, fiberness goes like something like that, like the blue rectangle. Braid positive links are fiber and are positive, so our result really extends his result. And in fact, we proved that there exist infinite links in this family that are fiber positive but are not braid positive. So this is really a generalization of his results. And what do we know? What is known for positive links? Okay, this is what we prove. But from the very beginning, from Kovanov's paper, original paper, it was known that below this row, everything is trivial, and to the left of the zero column, everything is trivial. This was known from the very beginning. Then it is known also that since positive links are semi-adequate, this row is also known, and this one, and this thing here, and this is not known, okay? So one may ask, okay, how good are these results? How good is this Covan of homology of positive links, just this little part that we know, how good it is to abstract positivity? So we did some experiments. So this is what we got. There are 2,977 prime knobs up to 12 crossings. 246 of them are either positive or negative, because everything I have presented you for positive links is exactly true by duality. If you, instead of minimal, go to maximal, you get the same for negative links, okay? So these results can also be applied can adapt to negative links. So what I was saying, 246 of them are positive or negative, and the other one are not. Okay, so with this obstruction, I told you, with this quantum homology table, we can extract all 2,731 knots up to 12 crossing for being positive or negative. So it seems that it's quite good up to 12 crossings. So then we say, okay, let's go to this census knots list, which are all hyperbolic knots whose complements can be triangulated by at most 9 tetrahedra. Here you have links whose diagrams have more than 300 crossings. I'm not saying that their crossing number is higher than 300. I'm saying that the minimal diagrams that are known for them has 300 crossings, okay? So this is like big family of complicated knots, not in terms of complement, but in terms of how diagrams look like. So we compute Cobana homology of 672 of them. Why? Because of computational abilities. We couldn't go further, okay? Computing Cobana homology is exponential. So we compute Cobana homology of these ones, and among these 334, it was known that they were either positive or negative, and for 338 of them, it was not known. So we pass this subtraction on Cobana homology, and we could abstract 329 of them from being positive or negative, and for 9 of them we could abstract, but it is not known whether they are positive or negative, so for these ones we don't know, okay? So this abstraction, this criteria is not perfect, of course, but I will say that it's quite good, okay? So this was about experimental data, and now, just to finish, I will tell you how we try to extend our results to other families of links. So this is the picture we have, this is the result we have, and for these ones, we have proved that first Cobana homology is trivial for positive and fiber links. So it's natural to say, okay, and what happens if I go to fiber and strongly quasi-positive, to the yellow square? Is this still true? Yes or no? What happened in this part here? So we consider torus link on 2 strands and 2G plus 1 twists. And if you compute, we consider this link, we consider it's 1 cable. We will go back later to cables, to the definition, but just we consider this link that we call KG, and these links are strongly quasi-positive. They are not positive, but they are fiber, meaning that they are exactly in the region that we want to consider. And we computed first Cobana homology, and it was not trivial. We computed this up to 200 for the same reason, because we don't know, there is no known method to compute Cobana homology of this cable, so we have to do with the computer, and we thought that 200 was okay for having 200 counterexamples of this, so we stop here, but in principle it can be true for any G, okay? So we saw that first Cobana homology is not trivial, so this is not true. If you have a strongly quasi-positive, you cannot extend the result there. So this was the first thing we tried. We say, okay, with a strongly quasi-positive, we cannot say that the result is true. Yeah, this was the reason why we stopped in 200. So then we say, okay, let's try to think in cables. And we say, if we have a knot, this is just a little bit of notation, because here is important what we call P and Q. I will tell you later, but if we have a knot, it's PQ cable that we will call KPQ. It's just the satellite knot having pattern the torus link PQ, and the companion is K. So just to get a diagram, this one is D, and you want a diagram of KPQ, just take P copies of D, do like the P copies, and then you have to add N twist, where N is P right of the diagram. Right is the number of positive minus the number of negative crossings of the diagram, minus Q, the Q that you use in when you say PQ cable. So P parallel copies of the link and N negative twist. And this negative is important because otherwise the extension we will do will be trivial, okay? So this N is negative. For example, if you have the trefoil knot, this has right 3 because it has 3 positive crossing. If you want to compute D39, you compute N is 3 times, the right is 3 minus 9, this is 0. So this is D39. This is a diagram of the 3-9 cable of the trefoil. Okay? If you want to compute if you want to compute D35, you just take the 3 copies, and now here we have to put some negative twists. How many of them? P is 3 times the right, which is 3, minus Q, which is 5, you get 4. So here you put 4 negative twists, okay? So what I want to stress here is that if K is positive, KPQ in general is not positive. So these cables in general are not positive. They are positive just in case Q is greater than PW. But in general, these cables are not positive links. Okay? So this was the result I told you before, the first one I told you about. And we prove that if instead of considering a positive link, we consider a positive knot, but here we compute first Covan homology of its PQ cable, the result is still true. Okay? If Q is greater or equal than P. So for this I was stressing that these are not always positive, because otherwise the result is trivial. This is positive, so of course it holds. You have proved it before. But these ones may not be positive. They are cables of positive knots, but these links doesn't have to be positive. Okay? So we could extend our result for the case of cables of positive links. And this was what we knew for positive links. So if we focus in these PQ cables, we prove that in fact this is true. So all of this is true for PQ cables of positive links. Okay? We had also this one. This was the second theorem, that if a link is positive, then its first Covan homology is trivial if and only if the link is fiber. So in fact this is true also for cables. If you have a positive knot and you consider its PQ cable, then the PQ cable is trivial if and only if the original knot is fiber. And well, we decided that let's see what's happened with L-space knots. L-space knots are those knots that admits a positive surgery to a Higar-Floer L-space. And they are fiber, they are strongly quasi-positive, and if you want to draw them in this picture, you will get something like this. Most L-space knots are known to be positive or even braid positive, and they can be not positive, but the only L-space knots that are not known to be positive are certain cables of L-space knots and an infinite family of hyperbolic links, okay? So I'm not saying that there are not more, but these are for the moments that are known to be in this region here, okay? So this was the result we have proved, the one I was telling you from the beginning. I will call this condition red star, okay? So we prove, as a corollary of one of the results I have told you about, that if you have an L-space knot and this knot is a cable of a positive knot, then it satisfies, it has Covan homology similar to that of positive links. And we also prove for this infinite family of hyperbolic L-space knots that are not positive, we also prove that you have this that their first Covan homology in small homological gradients have this shape. So we decided that in light of this result, we can conjecture that if K is an L-space knot, then its Covan homology in lower homological gradient should satisfy this way, meaning that it's similar to the Covan homology of positive fiber links. So this conjecture, of course, it is still open, and this was what I wanted to tell you about the talk. But since I have a little bit more time, I'm going to take 10 minutes to give you, to tell you about a combinatorial problem. Yeah, sorry?
Marithania, since you're ended up with this conjecture, have you checked this conjecture for the nodes on Snape census? So the Snape census you mentioned contains a bunch of L-space nodes. Have you checked all of these?
For the ones that we have compute Kobanov homology, yes. The problem is that we have compute Kobanov homology just of 670 something of them.
Yes,
so
sure.
the point is, for the big one, we haven't computed the homology.
Okay.
So, but yes, this is a good place to continue looking. So we have checked for the ones we know the homology. For some of them we don't know the homology. Okay. So for this one, not. Yeah. Any other? Before I go with the bonus?
So, is there any difference between reduced and unreduced Kobanov, or you are looking only at unreduced Kobanov?
No, I'm looking at the unreduced one, the original one. Yeah, unreduced. Yeah.
Will it continue for? Can we see a similar parallel for the reduced one also? I'm asking, because the floral homology are all related to the reduced Kobanov homology in some sense. So that's why I'm asking.
Okay. I understood now the why. So any other? No. Okay. So we go with the bonus. This problem is a problem that I will tell you why. Well, it is a combinatorial problem. It's something that anyone at high school can, well, maybe not at high school, but a first-year degree student can understand. Is combinatorial problem, and I like it very much because it's something I have been working it with Joseph Chitinsky. And the motivation for this problem, for me, I was studying Kobanov homology, and in my thesis, I gave a geometric realization of a special part of Kobanov homology, and I got some construction and got some simplicial complex. And later, talking with Joseph, so we started studying this simplicial complex, and is where the conjecture I'm going to tell you about appears. And it's a problem that I think is very hooking, you say, very that it traps you, and then you want to work on it because it seems super easy to be proven, but then nothing arises. And it has happened to me that I have speak about it in some conferences, and people have say, oh yes, this is very easy, my student will give a solution tomorrow, and then the next day there was no solution, neither the next one, and still is open. In fact, a proof of the conjecture appears in the archive, and after talking with the author about we found a mistake, it was wrong, so he had to remove the paper from the archive. So I want to tell you, I want to spread the word on this conjecture, because I will be happy if someone can either find a counterexample or find a solution to it. And the conjecture is the following one. So we have, imagine you have a circle, it has some chords, you draw some chords on it, and now we are going just to build a graph. So for each chord, just draw a vertex. So here you have 6 chords, 6 vertices, and now we are going to draw an edge connecting the endpoint, the vertices, if the corresponding chords, their endpoints alternate. You see, or in other words, if you cannot draw the chords in such a way that they don't intersect. Okay, so in this case, you see 1 and 2, their endpoints alternate, so I draw an edge. 2 and 3, they alternate, so you draw an edge, and so on. In this case, you have an hexagon, okay? So these graphs, the graphs arising that way are called circle graphs. And now from here, you are going to build some simplicial complex. And the simplexes here are going to be just the independent subsets of vertices of the graph. So, in this example, you always have the empty set, you always have the vertices, and now we need to look for pairs of vertices that are not neighbors. So 1, 2 are neighbors, so they are not here, but 1, 3, they are not neighbors, so they are here. 1, 4, 1, 5, 2, 5, 2, 4, 2, 5, 2, 6, and so on, right? Then you go to simplexes of dimension 2, so you need to find 3 vertices that are not neighbors. So 1, 3, 5, 2, 4, 6, and now you will go to look for simplexes of dimension 3, meaning 4 vertices that are not neighbors, but you cannot find them, so that's it. And if you compute the geometric realization of this, you will get this. Okay, so the two triangles and the edges. And the conjecture is that if you start with a circle with this chord and you do this construction, what you get here has the homotopy type of a wedge of spheres, possibly of different dimensions. Okay? In this case, you get S1 wedge S1. So this is the conjecture. It's very easy to be understood. It's super simple to explain, but finding a proof seems to be complicated. And just in very, very few words, why am I interested in this thing is because this is the result from some time ago from my thesis that I told you. If you start with a diagram, you can consider the zero smoothing, where you smooth everything with a zero, and always you know that you get a set of circles with the chords, some chords in the places where there was a crossing. So now, well, if you put here a straw and you blow, you will get something like this, okay? Here we see it's more visible how the chords, the blue chords are. So this, if you put everything inside, you get this example, and now you can do the construction I told you before. Well, here, you may have, when you do this, you may have different circles, so you just forget about the chords connecting different circles. Forget, if you have something like this, forget about this chord. Just consider the chords having both endpoints in the same circle. So you can do the construction I told you. From here, you just draw the graph, and from the graph, you construct the independence complex, okay? So you started with a diagram, you smooth everything following a zero label, and then you apply the construction I told you before. Just get the vertex, get the graph, get the complex, and what we prove together with my supervisors is that the extreme Kovanov complex of the diagram, meaning extreme means the lowest in Kovanov homology, you have the complexes, so just look for the lowest complex that is non-trivial, meaning the last one where you have something to study. So the Kovanov complex at this lowest quantum grading is a copy of the cohomology complex of this guy here. So if you want to compute Kovanov homology in this last row of the diagram, you can just compute the cohomology of this one. And in fact, later, together with Federico Cantero, we proved that this complex we built here is equivalent to, this is our construction, our initial, so this is Kovanov spectra by Lipschitz and Sarkar. If you look just at extreme quantum grading, I'm not saying in all gradings, just in this special lowest grading, this very easy complex is exactly Kovanov spectra. Okay, the geometric realization is exactly Kovanov spectra. They are equivalent. So this is the conjecture. If it were true, this would mean that in this lowest row you don't have torsion, because what you get here will be a wedge of spheres. And yeah, this is the bonus problem I wanted to tell about. And now, yes, Jean.
Questions?
Is there anything to know about homological degree other than 1?
About homological degrees, no, from 0, what is known, since the link is positive, you know that you have just a Z, but that's the 1 and 0 are the ones that are known for them. And for the rows, the same, because positive links are semi-adequate. So for semi-adequate links, you know like the lowest row and the second from the bottom row.
We know for almost extreme something.
Yes, this is the second, this is what I said, the second from the bottom, yeah, because it is semi-adequate.
Naive question, but so you studied positive, quasi-positive, positive links because they're the easiest ones to work with, or there's another underlying reason motivating you to study those particular links that apply somewhere else, or that have more richer structure, or is it just
So for us, the starting point was the paper by Marcos Tosik about arting positive braid positive links. So we say, okay, maybe we read the proof and we say, okay, maybe this proof can be extended. So the natural place to look for is if you have braid positive is positive. So this was the starting point, and for this we looked there. Then we tried for strongly quasi-positive, so it was not true. And the thing of putting this fiberness condition was because braid positive links, the one that Marco studied, are fiber. So for these ones, the condition was like you didn't need to ask for fiberness. But we found a paper by Stoimenov and Lizzie Buchanan saying that if a link is positive, then if a diagram is positive, then it represents a fiber knot or a fiber link if this reduced graph that I told you is a tree. So we read that, and it has nothing to do with apparently what we were doing, but we say, oh, this reduced graph, if it is a tree, is trivial, so if we can, so this was the reason why we put fiberness there. But also, having a criteria to extract positivity, I think is something nice, and we were surprised that for these knots, positivity is something that has been super studied, and that there were some knots that it was not known whether they were positive or not, and with this one could say, so it was kind of trying to extend his result, but then we were happy that this family was not artificial, it was something that makes sense to study.
Maybe I can say some history then and maybe some comments. So the reason why I did this is because I'm thinking the very second paper of Kovanov. So he has a paper, original one, and then the next one immediate with some computational results, and where he conjectures that the first group of positive braid knots, and it was on first very, very few experimental potentially is trivial. So that was my goal. Although it's much older than 2010, this is from my PhD. I didn't even know that it took that much time to publish. But I remember, so that is, how to say, Kovanov homology is a new invariant, which is very strong, and that was one of the showings that it detects something. So always for a new invariant, well, you want it to prove that it's something. In my case, I was lucky because the proof is, as you can see, rather elementary. The other thing is, as you can see also in my paper, I proved it also, the proof Kovanov-Rosansky.
Yes.
So basically for any...
But this one we tried to generalize, and we were not...
That's my first question. Does that
we
work?
tried it, and in fact, to be honest, we thought it is true, and we wrote it as kind of observation, like doing the same as in this paper, adapting it to this, blah, 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 it will work, but then we decided no. First, if we want to publish this, it had to be like very well written, like this paper, like step, like word by word what we do, blah, 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 and when we tried to do, it was super long, and at some point, not just long, but that we had to deal with some things that we say, well, we think they are easy, but we are not sure. So at some point we decided, okay, this will be a project, and now Nagesh, one of the authors, is working on that. So we think it is true, and computation suggests that it is true, but we don't have this in the paper. We don't have the actual proof. But yes, we think it can be also extended.
One thing historically now I remembered, so on my PhD defense, when there was discussion about this, they asked me, oh, did you think about quasi-positive knots, which is exactly what you were doing. Can you say something about quasi-positive? So the big one. So
Almost, no, quasi-positive, you mean?
Strongly quasi-positive knots. So
Oh, strongly quasi-positive.
So without fibered or something. Can you say something? So your theorem is for positive ones, like
Yes, for strongly quasi-positive is false. So for quasi-positive it should be false because...
yes.
So yes, it's false. This is...
No, it was just, well, I remember I never talked about
This
it.
one.
Like, yeah.
So this one are strongly quasi-positive. So yeah, if you remove fiber, still it is false. So So
maybe
this
something
one-
extra.
yes, this was the next natural place to look for, but this one was not true. So
And the question of Rama said, so not floor homology is good in detecting fiberness. So can you mix this with not floor homology, at least experimentally?
with not flow homology, we haven't tried to.
I don't know what it says about.
But for not flow, it detects fiber. Yeah.
It detects fiberness, and it's very simple for L. For your, you had also for L space. You have also the other diagram with L.
The L space, you mean? The,
L
what?
space knots. You also had later.
This one.
Yeah, I think it also has, it's very simple for L space knots, if I remember well. Not for homology.
Maybe, I don't know now, I cannot tell you.
So I think so. Maybe some mix of not floor and Covano. I think reduced Covano, by the way, should be very simple, very similar to this one as well.
I see.
So yeah, but I don't know what not floor is saying. So, but it is very computable again. So maybe you can plug it in. And compute.
Okay, so thank you. And also for your inspirational paper. For the
And also these positive rates are always alternating, or it can be non-alternating?
No.
They can be
You
non-alternating.
take any positive rates. You can take any sequence of sigmas, just positive, and close them. So it's very large. Yeah, it's very large group. But anyway, you also care about first homology group. You don't care about everything. So I think computationally that's not, well, for computer it's not that bad, right? Even for big knots.
Yes, it could be cut, but we didn't. I mean, yeah, we are just interested in the first two rows. Sorry, first two columns. Yeah.
Relatively small piece. So
Yeah, maybe we should go more into the computational to check the ones that are left as much as suggested from the census not list and check
What were you saying about hyperbolic knots? You said
that currently, or at least up to our knowledge, the only L space knots that are not known to be positive are some cables of L space knots and a family, which is infinite, of hyperbolic L space knots. So a family, I mean, one family living here, and for these ones we prove it, and we couldn't prove it for the cables of L space knots that lives here, but we prove it for cables of positive L space knots, which is not everything, of course, but for cables, the ones here that are cables of other here, so is why we think that this might be true, and the computational experiments that we have done suggest that this is true, but we don't know, maybe this false. For this is conjecture, yes.
and for them, I think non-floor homologists can say a lot. So well, at least computationally. So maybe some mix of these two things can stay.
Any other questions? If not, let's thank Marithania again. Recording.